Let's now move on to developing mole balances across our reactor spaces. We want to do this so that we can generalize the types of reactor, because so far the reactor types are quite restricted and quite idealized. We recognize that there may be situations where the change in moles due to reaction will influence our system hydrodynamics and our flow rates and so on. And this may lead to complications or inaccuracies even in terms of how these reactors perform. So let's move over to developing the mole balance for these systems. So from the last set of discussions, we had established these balances. So we had developed the mole balances or the design equations in terms of the concentration, and then we had also converted that to the conversion form, because quite often we could translate the reaction rate into a conversion, and so we could simplify or reduce the number of equations that needed to be solved to design that reactor. We had also established that for an elementary reaction, the reaction rate could be developed, or a formulation for the reaction rate could be established as the product of the concentrations raised to the stoichiometric coefficient multiplied with the rate constant. And so for this sulfur dioxide problem, where two molecules of sulfur dioxide react with oxygen to give us two molecules of sulfur trioxide, we could say that the rate of consumption of sulfur dioxide, and so that's how we read this. When we see the minus sign in front, we read that as a rate of consumption. So this rate of consumption is the rate constant. So that's some number that we have to find, and that's a strong function of temperature, an Arrhenius expression. So the rate constant multiplied with the concentration of the component raised to the stoichiometric coefficient. And that's multiplied with all the other reactants also raised to their stoichiometric coefficient. In this case, there's a 1. So for an elementary reaction, for the forward reaction, that's only in terms of the reactants there, so that's our rate expression. We had also said that the rate of reaction of any component could be equated to any of the other rates of appearance or disappearance, and the correction factor was introduced simply by dividing by the stoichiometric coefficient of that component. So we recognize that we are defining a reaction rate for the reaction, but when we define that, we always define it on the basis of some component. So we can say our reaction rate is the rate of disappearance of SO2, or instead we could write it as the rate of disappearance of oxygen, or we could write it as the rate of appearance of sulfur trioxide. So all these rates exist. However, they all refer to the same event. They are all referring to this conversion. So the formation of sulfur trioxide by SO2 and O2. So when they refer to the same event, then they are just different ways of observing the same change in the chemicals. And so there must exist a relationship among these three different ways of observing the same thing. And that's the relationship that we have here. And if we think about it, if we wanted to know the rate of SO2 compared with O2, if we look at just this part of the equation, we can see, according to this, the rate at which SO2 it disappears is equal to twice the rate at which O2 disappears. And if you look here, you can see that's true. Whatever this rate is, this disappearance is twice the rate of that. So this agrees with what we expect there. And in a similar way, we can say that the rate of formation of O2 must be twice the rate of disappearance of O2. So SO3 is formed twice as fast as O2 is consumed, and it's formed at the same rate at which SO2 is consumed. So this very much agrees with what we expect here. So that's an important thing to establish for developing our mole balance. And now let's look at conversion. So we had defined conversion in a general way. We had defined conversion in terms of any component I in our reactor. And now we are going to consider that conversion in terms of a reference amount. So when we talk about conversion, we are always talking about some quantity that's been converted into some other quantity. So in this case, we have, if it's a CSDR, then we have a flow that's entering here, and then there's some reaction, and then there's a different flow of our component coming out here. So in this case, we can say the conversion must be based on the amount of the component that's entering here. And you see that's different for each reactor type. So for a batch reactor, instead, we would say the conversion of a component will depend on the initial amount that we put in the reactor. So if it's a batch reactor, we don't have these flows here, then we can't talk about a concentration here. Instead, we have to talk about an initial amount in the reactor. So here, if we take this as a generalization of our sulfur trioxide reaction equation, if we are talking about conversion in the general sense, we recognize that there has to be some reference amount. So whether we think of that as an inlet amount or an initial amount, there's some reference amount of a component, and then there is some current amount or there's some exit amount, and so that's how we can define conversion in the abstract. If, of course, the volume is the same before and after, then we can divide volume in the numerator and denominators here, and so we can write this in terms of concentrations instead. So if we have that, if this is true, then we can say that the concentration can be expressed as the reference concentration multiplied with 1 minus XA. So 1 minus here and then multiplied with the reference amount. That's generally true for any component. Right? We can write its current amount in terms of its entering amount or its initial amount multiplied by 1 minus conversion. So remember, conversion is how much has been converted. So 1 minus that amount is how much is left over, or the fraction that's left over. So the fraction left over multiplied with the initial amount or the inlet amount, that must be the amount that's left over in the reactor. Right, so that's generally true. And then we can think about in our reactor, if we just think about component A and B reacting, and we are talking now specifically about this, we can see that, as we said already, twice as much of A being converted is equal to the amount of B that's converted. So the amount of B that's converted, we can say, is the initial or inlet amount subtracted from the amount that's currently there. So the initial amount minus the current amount, that must be the amount that was converted. Right, so just think about that for a second. This must be the amount that was converted. Right, your initial amount minus your current amount must be the amount that did react. So twice the amount that did react for component B must equal the amount of A that did react. So this is the amount of A that was there initially or at the inlet, and this is the amount that's currently there. So the difference between those must be the amount of A that did react. So we can then justify that these two amounts must be equal. And then we can go on and relate the amount that did react in terms of the conversion. So we know that the amount of A that did react can also be obtained by taking the initial amount multiplied with the conversion. Right, and so you could write this part directly from your definition of conversion that's already said here in a way. Okay, so that's there, and then we can just rewrite this expression in terms of component B. So we can say concentration of B must be, and so we take the 2 across on this side, so we divide by 2, so XA over 2 CA ref, and then we move that CB ref here. So the amount of B currently in the reactor is the initial amount or inlet amount minus the amount of A that reacted divided by 2. So A is disappearing twice as fast as B, so the disappearance of A divided by 2 is the amount of B that was lost. So the initial or inlet amount minus the amount lost is the amount left over in the reactor. So these are all different ways of saying the same thing. Now we can also say the amount of C that formed, right? And we can say the current amount minus the inlet amount, that's the amount of C that formed. So for C, it's a little different. C is the product. So C doesn't enter the reactor. And so generally we would think of this as a number at 0. But we keep this here because perhaps there's recycle in the system, or for whatever reason we are feeding product into the reactor. But generally we think of this as being equal to 0. So the amount of C that formed is the current amount there minus the amount that entered, and that amount is equal to the amount of A that got converted. So that's the amount of A that started, and that's what we're left with, and so on. So this is pretty much the same as what we saw for component B. So again, we can rewrite this in terms of the conversion of A. So we can just take C ref onto that side. And so obviously these are all simple things. We can see all this quite directly, but there is a reason we are trying to generalize our expression. So we have this expression, and now we are going to introduce this notation, capital theta sub I is equal to the reference concentration divided specifically by component A concentration as the reference. So here we are specifying our concentration at the inlet or initially on the basis of component A. And of course, this is an arbitrary choice. We could pick any component that participates in this reaction. In this case, we often pick the component, the reacting component, and sometimes we can identify a kind of primary reacting component. So we define our theta in terms of some chosen component. And so don't stress too much about this choice, but we can choose any basis component for defining our theta. So it's just a ratio of the initial or inlet amount of the component I divided by the selected basis component and its reference value. So with this definition, we can see now that we can write this nice general form for our concentration. So if you look back at each of our expressions, for CC, we had CC ref, and we can see that CC ref is equal to theta C times CA ref. So theta I times CA ref is going to be the first term. So that's what we can see in the general expression. The reference amount times theta I, that seems to fit what we have for component C here. And then if we look back at component B, you can see here that we have CB ref, and we know CB ref is theta B multiplied with CA ref. And so both components seem to fit with this. We can also talk about A. So if this is simply CA, then theta I equals 1, right? It's going to be CA ref over CA ref, which is 1. So 1 times CA ref. We know for component A, the first term is going to be a CA ref there. So this part of the expression seems to fit all three relationships. And then we can think about the second term as well. So if we're talking about CC, so we found here CC equals CA ref XA. And if you substitute here the stoichiometric coefficients, so CC equals plus 2, and nu C equals plus 2. Oops. Nu C equals plus 2, and nu A equals minus 2. Right, so plus 2 over minus 2 is minus 1, and then times minus is a plus 1. And so we can see plus 1 XA times CA ref, which is on the outside here. And in fact, let's just go quickly back here to see that. So we know the reactants, we read this coefficient as a -2. So nu A is -2. The coefficient here is -1, so nu B is -1. And then this is a product, so this the nu C is +2. Right, so those are our stoichiometric coefficients. So it seems to agree for component C. And then for component B, we know this is nu B is equal to -1, and nu A is -2. So this is -1/2. And if we go back here, we can see that we've got -1/2 Ca ref times Xa. And so component B also fits this expression. Of course, we can also think about it for component A. So if it's Ca, then this is nu A over nu A, which is clearly 1. So this becomes, and we said this was 1, so this is 1 minus Xa times Ca ref. So that's very much straight from the definition of conversion. So for component A, we had that expression as well. So this is a nice general expression that we can use for any component in a given reaction. Right, so we can now exploit this, and so use that to translate all our concentrations in our reaction expression into conversion. So we said because it's an elementary reaction, we have this expression. And of course, even if it's not an elementary reaction, if there are a bunch of hidden steps that we don't know about, but still we can go ahead and do some experiments in the lab and figure out a rate expression here, then as long as we've got K times some product of concentrations, we can still go ahead and apply this formulation and translate each of those concentrations into conversions. So I'm just saying here that applying this doesn't require that we have an elementary or non-elementary reaction. So this will work for any reaction as long as, it's so this just generally works as long as we can define the conversion. So anyway, for component A, we know this is going to be Ca ref times 1 minus Xa. So, Ca ref squared times 1 minus Xa squared. So here's the 1 minus Xa squared. And then there's a Ca ref squared. And then we'll get another Ca ref from the Cb part. So we'll get Ca ref cubed. And then the Cb part, we know is theta b minus Xa over 2. So there you go. You've got now the rate of consumption of component A expressed entirely as a conversion. And yes, you can see a concentration over here, but we do regard this as an easier concentration to work with. So this concentration is something like our inlet or our initial amount. So we think of this concentration as being under our control, because we are free to choose what the inlet concentration might be, or we are free to dictate what the initial amount of concentration is in the reactor. That's because we load up the reactor with component A and we let it react. So we are in control of this. So we think of this as a number that we know, and then everything else here is just the variable Xa. Theta b, of course, is based on the amount of B that we put in. So in a similar way for Ca ref, we can control theta B, we can control the amount of B we put into the reactor. So in effect, we've totally transformed this mysterious conversion rate, right? We didn't know how to express our reaction rate expression, but now we have a nice way of relating it to the conversion. And you see then that if we take any of our rate expressions, right, let's go back here. If you take any of these, if you take any reactor, we've got these relationships, and we had defined Ri, but now we have an expression for Ri. Now we can rewrite Ri in terms of the conversion. And so we are getting another step closer to being able to solve these equations. Right, because now the equation is totally in terms of xi, and so we can just go ahead and solve these equations for xi. So in other words, we are now able to calculate what the conversion is going to be from that reactor. And of course, it's going to be influenced by the parameters. It's going to be influenced by how much time has passed. It's going to be influenced by what the initial amounts are that we put into the reactor, or what the inlet concentrations are, and so on. But all those are under our control. So as engineers, we are the ones saying, yes, go ahead and load that reactor with 50 moles or whatever it is. And so we are now closer to the type of thing we like to work with. We are specifying how that unit is going to operate. We choose the time and the feed amounts, and then yes, nature plays its role. Nature is dictating the rate at which the reaction happens, but at the same time, we are now able to estimate how nature is going to do that. We can estimate a number that nature is going to work with or work at in terms of variables that we can work with. So we can work with conversions, and so that's what nature is going to have there, or that's how we can read what nature is going to do. Okay, so for this specific exercise, then we can write all these balances, and we can just solve for XA, and then that tells us, or that helps us design our reactor. And that's pretty much it. Yes, here I'm saying that, you see, we can just go ahead and solve this one equation for XA. So in each case, we can solve one equation. We don't have to do this for every single component. You don't have to write dxb d tau equals blah, blah, blah. You can just go ahead and solve for XA. And then because we have this nice mole balance, we can just go ahead and use the value that we obtained from solving these equations for XA here. And then we just stick in all these other constants, and that will tell us what the concentrations are of all the other species. So it might occur to you, well, I don't care about this. These are the reactants. What I really want to know is, what's my concentration of the product coming out? So if you do solve this, you can still work out what Cc is. You just go ahead and stick in theta c here. That's probably 0. And then nu c, which is +2, and nu a is -2, and then the value for xa, and then that tells you what your product concentration is. Okay, so now we are actually able to solve these equations, and so please go ahead and take the next step in the exercise and solve the three balances, and do it for all three species using this, and yeah, for that same sulfur dioxide problem. Right, you can use the same kinetic rate constant as was given to you in the previous chapter. Okay, now all this looks quite straightforward, and it seems like we've completely solved the problem. However, there are a number of implicit assumptions that we've been making. So for instance, we've been assuming that we can just cancel out the volume, right? We started out saying this. We said, oh yeah, if the volume can be taken as approximately constant, then we can simply just go ahead and divide the number of moles by volume, and then we can just rewrite it in terms of concentration. Now, that is sometimes true, but often in engineering problems, it turns out not to be true. And let's think about generalizing our expressions so that they apply to more situations. And in fact, that's the general approach taken in this course, right? In this course, we start out with some formulation or some framework that helps us estimate the reaction rate and helps us write a mole balance, and we do it in a very simple situation. And then we start thinking about, in industry, what really goes on there? Is it really as nicely behaved as we are claiming it to be? And so we then think about how do we extend our theory so that it applies to a complication that we hadn't really accounted for by making all the assumptions that we had. And I haven't said enough so far that that we have gone ahead and applied a major assumption, which is that the temperature is constant at all times. So far, we haven't dealt at all with the energy balance. We've just assumed that the temperature is constant. And so that's one of the things that we are going to generalize. Not right now. In a couple of lectures, we'll get there. For now, we want to think about this issue of the volume and just assuming that we can go ahead and cancel volumes. And let's think about the gas phase reaction. So we know that this is in line with the exercise that we've been talking about. And if you think about what's going on here, you are taking two molecules and reacting them with one molecule and getting back two molecules. And so three molecules are becoming two molecules. And if you think about that happening, let's say, in a glass jar, that means that you are losing molecules overall. Of course, the mass is staying the same, right? C is bigger than A and B. It has more oxygen in it. But still, in terms of the number of molecules banging around in your space, you will have less molecules, right? You'll have 2/3 less molecules. Let's say totally reacts, then you'll have 2/3 less molecules. So that is a loss of pressure through your system. And so this reaction, right, in this specific case, and it's not always, I mean, this could have been 4C. So there are other reactions where the pressure will increase. So in this specific reaction, the pressure is decreasing. And if the pressure decreases and if it is a gas phase reaction, then that means we are going to have a change in the hydrodynamics of our system. So when we drew our nice diagrams that showed the flow of our species, where it was showing, let's see if we can pull it up here. If we have this vessel and if the pressure is reducing here, then we have to be concerned, number one, about safety issues. That is, this are the walls of this vessel going to hold up? Once the conversion goes very high, we will have a specific loss of pressure here, and that might cause this vessel to buckle. So number one, we have to think about safety concerns. In a flow system, we have said that there's a nice steady state if we assume the flow in and the flow out is equal. Now, if the pressure is dropping, then that's going to influence our flow through here, right? There's no magic instrument that's going to just keep the pressure constant here. Well, other than a controller. But for now, let's say we don't have a controller in here. So if your reaction is dropping the pressure, that means necessarily your flow rate out here is going to be lower than the flow rate in here, right? You can think of the reaction as sucking in part of the some of the molecules coming through here. And so you will have a lower flow rate through here. And you see, automatically then that throws out everything we've done in terms of our material balance. Well, not quite. We'll look at how we can modify what we are doing to account for this pressure drop. And so the same applies in the case of our plug flow reactor. We are assuming that there's a nice steady velocity across, right? Our whole development was in terms of a constant velocity across here. But if we have a developing pressure gradient, if there's a loss of pressure through here, then our flow rate, our velocity is not going to be constant. So let's look at how we can design around that. So coming back to what we're looking at here, let's start with the batch case. And let's think about, first off, we spoke quite abstractly when we were defining our reference flow ratio. So in the batch case, we are not talking about flow, right? By definition, there's no flow through a batch reactor, so we just talk in terms of number of moles. And in this case also, because there's no flow, we are not talking about inlet. We are talking about the initial amount with respect to the basis component. So in the case of the batch reactor, the version of theta I looks like this. It's going to be your initial number of moles in the reactor for component I divided by the initial number of moles of component A, or whatever basis you choose, in the reactor. So that's theta I. And we recognize here, we did say this, that that by definition theta A equals 1, and usually for a component that is not present initially, like a product, then theta I equals 0. So anyway, initially we have NA naught is theta A NA naught, NB naught is theta B NA naught, NC naught is theta C NA naught. And so if we add up all those amounts, that's the amount that we have initially in the reactor. And then in terms of the change, A reacts, so it's converted. So just rewriting in terms of conversion, we know component B is converted half as fast as component A. And then we know that component C is formed in the same amounts that component A is consumed. So those are the three species, and we can rewrite this in terms of stoichiometric ratios. So we had talked about that nu I over nu A, that's basically taking care of these ratios in front here. And so we had shown that this is the change that we observe. And then the amount that's left over in the batch reactor, if we just add together all these, right? So just adding these two directly together, you can see these forms. And of course, we can also just use our general expression. So the general expression applies in each case. We just have to update I over here. So it's A in this case, B in this case, C in this case. So that's our nice general expression. And then we can just add all these up, and then we can say our eventual number of moles in the batch reactor is the sum of all these. And so it's simply Na naught and then the sum of this stuff here. So we can then estimate the mole fraction of component I as, so any component, we can just take its current amount or its final amount and then divide it by the total amount. So clearly Na naught is going to cancel, leaving us with this factor divided by this one. So we can estimate the mole fraction when given the conversion at any stage. And so you can also then easily say that if we have complete conversion, right? If component A is completely converted, then XA equals 1, and so we can then estimate what our final mole fractions will be for everything in the event of complete conversion. Of course, how much you do convert does depend on how long you allow this reaction to continue in your reactor. And as the engineer or the operator of that reactor, you can choose, well, maybe it's just 1 hour. And so we can solve our batch balance and estimate after 1 hour what the conversion is going to be, and hence what the mole fraction is. Okay, so that's how we can estimate the mole fraction. And in fact, all this is more for the sake of practice, because you could, of course, have jumped straight to this result. You could have said, look, I have faith in my general expression here. Nothing that we've said about this batch reactor, even in terms of pressure, influences anything there. And especially given that the batch reactor is not in flow, so fine, the pressure can go up, but the number of moles is what it is, dependent only on the reaction rate. And so I'm not worried about all that, and so I'm just going to go ahead and use this. So you could have just anticipated this result, but we did it sort of for practice right now. Now let's look at a case where it does make a difference. Okay, now let's look at a non-equimolar reaction, right? The same non-equimolar reaction. Let's look at this reaction in the context of a CSTR or PFR, and let's think about how we can estimate the volumetric flow rate, right? So now let's imagine what's going to happen in this reactor. So let's say now that we have in our reactor, we've applied a pressure of 3 atmospheres here, and we know that the pressure is going to drop here because the number of moles or the number of molecules is going to reduce. So the pressure here is going to be, the pressure here would tend to be lower than the pressure there. And now we know that flow rate is a function of pressure, and it's a function of pressure difference. So if there is a flow or a tendency for pressure to reduce here, then the flow rate will simply reduce. So the flow rate here will be lower than the flow rate here, and that will happen. It will keep reducing in flow rate until the pressures equalize, right? Or let's say that it does. Let's say this is a perfectly frictionless system, and the flow rate reduces until the pressure is the same across that reactor. So this is one of the assumptions that we could apply, and of course we can go and test that and so on. But generally, we know from our fluid mechanics that if we have an applied pressure, and if there's a lower pressure in one line compared with the other across the same space, then what tends to happen is that the pressure, or rather the flow rate, will change such that the pressure becomes the same. Right? So if the pressure becomes the same, then we can establish a relationship between the flow rates. And as a starting point, let's first talk about how we can relate pressure to number of moles. And of course, we would use the equation of state for that. So from thermodynamics, we know that if your pressure is less than 15 atmospheres, then we can write PV equals nRT, right? The ideal gas law applies as our equation of state. And of course, if it's more than 15 atmospheres, then another equation of state applies, and you can go ahead and use the appropriate equation of state. So for simplicity, we'll just use this one, noting that you can always update all the developments which follow for any equation of state. So in the batch system, we would write this, right? In the batch case, there's no flow to worry about. So volume is a certain value and number of moles is a certain value. On the other hand, if we have a flow system, and right now we are talking about CSTR and PFR, we've already dealt with the batch case. So in a flow case, then instead of a volume here, we could talk instead in terms of the volumetric flow rates, and instead of a fixed number of moles, we can talk about a molar flow rate. Of course, we can still write this balance or use this equation of state on the reactor itself. So on the CSTR, we could apply this. But instead, let's write about the equation of state in the pipeline at the point of entry and at the point of exit from that reactor. So at the point of entry, we can write in terms of flow, we can say the pressure multiplied by the volumetric flow in is equal to the number of moles flowing in multiplied by RT, universal gas constant, 8.314 times T. So that's the same equation of state. And then, of course, RT are constants with respect to the component. So we can rewrite F in terms of the individual species just by adding them together. So this is the equation of state written at the inlet point, and then equivalently we can do exactly the same thing at the exit point. Right, so those two are true for this condition, right? And you can find the equivalent form for any other pressure, for higher values of pressure. Now, we have said that we are going to assume that the pressure is constant. In other words, the flow rate adjusts itself. Your exit flow rate is going to adjust itself until the pressures become equal. So if the pressures are equal, then we can solve both these for pressure. So clearly you can take this thing divided by Q in, and then that divided by Q in. And so we can say those two things must be equal. And now, of course, we have this nice relationship, the nice mole balance that we can rewrite for F out. And so we can then substitute for F out in this expression. I see here before I did that, I just rewrote this in terms of Q out. So you can multiply Q out and then divide by this. And then you get Q out equals Q in times this ratio. So this is all nothing but this thing here rearranged. Right, and here I didn't specify, I should have said here T in and T out, right? So just make that correction, please, T in and T out. And so we would write that like so. Now, we did also say that we are using the isothermal assumption for now, and we would later on generalize and relax that assumption. So for now, isothermal operation means T out equals T in. So those two can cancel. Then, of course, this is the universal gas constant that can also cancel, leaving us just with the ratio of F out over F in. So Q out equals Q in times F out over F in, and that's where we are just substituting our mole expression for F out and F in. Right, and then the FA ins can cancel, leaving us with this nice expression. So this can now be used for us to estimate what the exit volumetric flow rate will be. Right, so that's all we need now. We can go back to our balance. So going all the way back here, when we write our balance on the CSTR or PFR, we don't use this expression anymore. We have to go all the way back here, and we update our mole balance to say, well, for the CSTR, Q in is no longer equal to Q out, right? The volume is still constant, but these two are no longer the same. And Q in is considered under our control, and so we regard this as a known constant, or it's known even as a time function. We specify what flow rate we are feeding that reactor at. But our concern was we didn't know what the flow rate coming out of that reactor was going to be. But now we have estimated it, right? We've said now that we know how to estimate what our exit flow rate is, and that is purely a function of the current conversion. And of course, that is the variable of the equation anyway. So we had said we can rewrite this whole balance in terms of XA. So we had translated this whole thing into a conversion. And so that conversion now applies even in terms of Q out. Right, so that's how we can update our balance and account for non-equimolar flow even in this complicated gas phase situation. Right, so that's how we can generalize that. And of course, we've been talking quite theoretically so far, but we will obviously come back and do a number of examples around this. Okay, so that's one of the first generalizations. Now that is all referring to the gas phase. Let's think also about our liquid phase in the reactor. And of course, liquids being approximately incompressible, the reaction itself is not really going to change the liquid volume by much, right? When species are in the liquid phase, the volume that they exert, right? If you want to think about it that way, the volume that they exert doesn't influence the bulk liquid as much as it does in the gas phase. In the gas phase, with the molecules freer to move around, yes, there is this volume expansion amount. But in the liquid, we don't really see that happening. The change is so slight, so negligible, that we are not really worried about the reaction influencing our reactor volume. However, the reactor volume can change purely because our flow rates are not necessarily nice and equal or even constant. And remember, when we did the development for the CSTR, that was one of our big assumptions, right? When developing the steady state equation, we had made the assumption that Q in equals Q out equals Q. So here well, anyway, you get what I'm saying. That we had used that approximation Q in equals Q out equals Q, and then we could divide by V and rewrite in terms of the space-time. So, well, here it is. Right, so that was the approximation that we made in order to develop these nice balances. However, it's not generally true in industry. And so we have to be careful about the equation that we are developing and for what purpose it's going to be used. Now, if we are doing all this just to design the reactor, then that's fine, right? In our reactor design, we are typically thinking about how the whole process is going to operate and how over several years we plan for this process to operate at this given production rate, and we know that on average there will be this flow rate coming into the system. And so at the design phase, we are not really bothered about unsteady influence. And yes, we'll put in a control system in anticipation of needing to attend to unsteady behavior. But overall, we are designing a reactor for a certain capacity, for a certain amount of conversion, and so on. So at the design stage, we are not really thinking about unsteady flows where Q in is not equal to Q out even. But when we actually operate the reactor, it's hardly ever the case that we are going to stay to a fixed Q in and Q out. Right? If you go and walk into the control room at any chemicals process, you are going to see graphs with values oscillating wildly. So you may have sat in your design office and said, okay, the flow rate here is going to be 7 kilograms per second, and that is how this process must operate. But once the thing is constructed, and if you go and wander into the control room, you'll find the thing oscillating through crazy numbers from sometimes on orders, more than one different from what you've designed it for. So in the industry operation of your reactor, we have to acknowledge these two are not going to be equal and they are not going to be time constants. So this is not exactly a problem that applies at the design stage, but still we need to be able to design around this. And so later on in your controls course, and there is in my set of videos, there is a playlist on frequency domain dynamics and how you can design for these unsteady behaviors. So you can have a look on the YouTube channel for that. But for right now, let's just say we are going to consider that flow rates are not constant. So we need to relax this assumption that the volume is going to be constant. So remember, we are talking now about liquid phase, and in the liquid phase, we are concerned with the reaction volume being the liquid, and that liquid volume is dictated by the level in the tank. And it's not the same as the case of the gas reaction. So if it's a gas reaction, that gas is obviously going to fill the whole container. So the gas will occupy all the available volume, and there you can. So even if your flow rates are changing in the gas phase, the volume is staying constant, right? That's something that does influence our development in the previous section where we were talking about the volume pressure change. So in the gas phase, the pressure changes here, but the volume doesn't really change, right? In the liquid case, if you are feeding your liquid in here, then that liquid is going to join some pool of liquid down here, and you are withdrawing from that pool of liquid another stream of liquid there. And as you change these flow rates, then that level is going to go up and down in this in this vessel. And if the level goes up, and maybe if there's more reactant, if you've added a lot of reactant that caused the level to go up, then that means the concentration of your other species become effectively diluted to some extent. Or if the level goes down, then it's more concentrated. So that is going to change the concentration in the reactor, and that's going to complicate our efforts to identify a reaction rate and so on. So we do have to account carefully for the influence of volume change due to changes or differences between the flow rates and changes over time. right? So that's why we are doing this. And let's go back here, all right? So the first thing we can do is just think about the total mass change in that reactor. So we can write a total mass balance. We can say the rate of change of mass in this liquid phase is equal to the rate of mass that flows in minus the rate of the rate at which mass flows out. And so that difference is clearly the rate of change of mass in the reaction space. And then, of course, we really want to know how the volume is changing. So we can do that through the density. So instead of writing in terms of mass, we can say that mass equals the density in the reactor multiplied by the volume in the reactor or of the reaction space. And again, to say it more explicitly, the reaction volume might not be the same as the reactor volume. So the reactor volume might be 50 cubic meters, but your liquid in that reactor might only be 40 cubic meters. And so that's why we are doing this. The level might be changing, so we need to know how this volume is changing. So anyway, that's there. Then your inlet mass flow rate will equal your inlet volumetric flow rate multiplied with the density of your inlet stream. So that's an estimate of your mass flow in. And then your exit mass loss is equal to your volumetric flow rate at the exit point multiplied with the density at the exit point. And then if this is all happening in the liquid phase, quite often we can make the approximation that the density inside of the reactor is equal to the density at the inlet point and is equal to the density at the exit point. And so all these densities are the same, so we can just cancel them out. And then we can write that the rate of change of the volume of the reaction space in the reactor is equal to the rate at which we are volumetrically feeding into the reactor minus the rate at which we are withdrawing from the reactor the volume. Right, so this is a balance then on the volume. Now, if we go back to our material balance on the CSTR, right, when we applied perfect mixing, remember the integral on Ri in V simplified to Ri times V. So that's the only assumption that's made here so far, right? In all these terms, this is just dNi dt rewritten in terms of concentration and volume. This is your inlet molar flow, outlet molar flow. So we haven't applied any other approximation than perfect mixing. So even if our flow rates are not equal and maybe changing in time, still we can say, well, in that reactor, it's perfectly mixed. There's enough agitation that even though the flow rates are not nice and constant, still we are assuming that perfect mixing applies. So we retain this and we don't make any other simplification. Now, the thing we cannot do is just divide by V. Right, before we said V was constant here, we could take V out as a constant and just divide that V, divide Q by V and cancel that V there. Now we can't do that, right? This V is changing in time according to these flow rates. So we have to acknowledge V is a time function. Then of course, concentration may also be a time function. And so both these time functions are multiplied together, so we can use the product rule of differentiation and separate it out. So ddt of civ can be rewritten as v dci dt times ci dv dt. So that's there. Right, so we've just expanded on the left-hand side here. All this stays the same. And now we can say, well, dv dt, we do know what that is. From our overall material balance, we can go ahead and just substitute for dv dt. So fine, this is an actual operation on V, but still we know how to estimate this as a number. So we can substitute this difference for dv dt in this first term on the left-hand side, and then everything else we just leave as it is. So that's there. And then if you look at this term compared with these terms, there are some similarities, some common factors there. So you've got Q in and Q out. So let's try grouping it in terms of Q in and Q out. And you'll find here that, well, let's look at it back here. So you'll find that, of course, your your Q in, so if you group for Q in, you're going to get Ci in minus Ci. So if you take that Q in term across here, that's what you'll get. And then for Q out, you've got minus Ci Q out, and you've got a minus Ci Q out on this side as well. So this thing can cancel with this thing. So this term actually vanishes. And so on the right-hand side, we are only left with Ci in minus Ci times Q in, and then that's the only other term, Riv. Right, so we no longer have a Q out term here in this situation. Okay, and then you can now divide by V. So fine, we do know V is changing in time, but we've extracted it out of the DDT. So now we have the same volume changing in time, so we can divide through by V. And then Q in, we do have to divide by V here. So we can rewrite this equation a little more simply like this. Right, now to solve this equation, you've got Ci as the variable of the equation, but Q in is some time function, and in response V is also a time function. So we know Q in we can specify as a time function, but V needs to be solved for, and we have the balance that we can use to solve for that V. So anyway, we can keep dv dt as another equation, and then this equation, of course, we have to keep that. That's what we are interested in. Okay, so in other words, if we know Q in and Q out as time functions, we can solve for this, and so we can get V of t, and then we've got Q in of t. This we know we'll write in terms of concentrations, and so then we have everything we need in the set of equations to solve for this reactor. And that's basically it. So in this session, it's fairly theoretical. We are just establishing all the relationships, and through the exercises we'll gain some practice in actually solving these equations and getting some numbers out.